Carry on.
Yeah, so this is about CAP Theorem. I'm going to introduce you how each and every letter of CAP Theorem works. So normally we think that C stands for consistency, but there is something called linearizability. So originally, CAP Theorem was proposed as a thumb rule without any precise definition. Okay. So the CAP theorem was formally defined to a very narrow scope. It only considered one consistency model and one kind of fault tolerant that is called. It considered only network partition. So like whether the node is live or it is and it is disconnected from other nodes. So the other problem is the CAP theorem does not speaks about network delay or dead nodes or other trade-off. It just speaks about a very narrow, specific thing like consistency model and network partition. That's it. So in the consistency, right, as per C, right. So say that in a distributed system, you have a right factor of 2. Say you tell that the right factor is 2, and if those two nodes are satisfied, then we tell that the two nodes are satisfied, then we tell it is consistent. So in this diagram, if you see right, so this node is the red one is not written. But these two nodes for the right factor of 2, we tell that this node gets written and this node gets written. And it tells an acknowledgement to the master saying that, master node saying that, yeah, these two replicas are being written. Then we tell that the data is consistent. In the later point, the node which is in red, right, which is in red node, which can come as get synced up. Once it gets synced up, so now the data becomes consistent across everywhere. But in a distributed system, we give a factor and we tell that that factor is met, then we tell consistency. Linearizability is something which I would speak in the coming up slide. But how do we achieve the consistency, right? So there are in the RDBMS side, it's completely different, whereas in the distributed side, it's completely different. When we speak about consistency, we need to see whether we are speaking about from a distributed side or from an RDBMS side. So RDBMS by nature gives you atomicity, which is very atomic to each and every transaction. So you have isolation levels where you have a very defined consistency where you can achieve strict consistency, high level of consistency you can achieve. But whereas in the distributed environment, it's not the same. It is completely different. Where you can define how many nodes can be written, and then those nodes are written completely, then you tell it's consistent. And if other nodes say that there are 10 nodes and you give a factor of just 2 or 3, and those 3 nodes are written and acknowledged to the master, then you tell it's consistent. But whereas the other nodes can get later replicated. So that's how we achieve consistency in the distributed system. We will not speak about eventual consistency. That's a totally different topic altogether. How to achieve eventual consistency and all that. So linearizability is like it's very much connected with the consistency. So under linearizability, right? Say that. Once we tell linearizable, there are a lot of other things come under linearizable. I would show you the diagram of that. So say that in a linearizable, right, or you can tell it as consistency. Say that at t0, a dog, we have a state saying that the dog is hungry. And at t1, there was an update saying that the dog state is full. So all the nodes must have t1 state, and you're not allowed to go to the you're not allowed to show to the client that the dog is hungry. That is, once you tell it is consistent, then you cannot flow back in time. So The problem in the distributed environment, right? It's very hard to achieve certain states because if you start putting consistency, then you would have a performance hit. All this comes in inevitably if you start introducing linearizability or consistency into your system, because say that a person in New York, right, and to New York, but in the London, right, it does not get updated. But someone reads the data from London, he would see a older state of the data, even though you tell consistency, he would read the older state of the data. So that's the problem here, and that happens because of the replication lag. And yeah, how much ever, because the data is flowed at the speed of the light, but still there's upper limit, right? Upper bound, physical upper bound is there, right? So there, in the distributed system, there are certain problems. So we need to decide how are we going to have consistency. So any question in this thing?
How do we decide the right factor?
Right factor is, it's up to us to decide. Say for Cassandra, right? So that's what I told, the Byzantine problem, right? Where normally the right factor is decided by W plus R. It should be greater than the number of nodes. Say that you have n nodes, then your quorum should be something like normally it is 3. You can have more than 3. Once you start increasing more than 3, right, your performance will start getting introduced. Say the recommended one by the Cassandra is normally right factor of 3. For 3 nodes has to acknowledge that it has the latest data to the master, and then only it sends back an acknowledgement. If you start increasing that number of right factors, that then you'll start having performance hits on that. So the right factor has to be decided based on your application. How are you going to decide whether you want strong consistency, or you can have weak consistency or eventual consistency? All this can be decided by discussion or brainstorming within the product that you're trying to build.
Okay.
So one question here, Manoj.
Yes.
Once you are talking about consistency, means that, and you talked about that you talked about strong consistency, eventual consistency. So once we are doing the writing means once you are writing to any database or any documents, we are writing it. So in that case, what we have to go and we have to write every notes, or it is a replication will do that in the background to.
Okay, so
To write.
that's what I told, right? So when you tell right factor of 2, 2 nodes have to get written by the master. Master has to get an acknowledgement from those 2 nodes. This third node, right, which is in red, eventually, actually, I think this is a mistake here. It should be ln. Yeah, so the third node gets replicated. The third node eventually becomes available, consistent. Okay.
Okay. So you want to say that okay, first it is writing into the master, and then from the master that all the right factor, whatever right factor you have you have associated on that basis, the replication is happening across the nodes.
Yeah. See, majority of the nodes, majority of the accepted nodes have the same value. That's the bottom line. So we tell that when we tell the right factor is 2, then all the 2 nodes, right, in your system should acknowledge saying that I'm having the latest data to the master, and then the master would send back the acknowledgement saying that it is it's successfully written. So we are defining the consistency level in a distributed system. Okay, but whereas in an RDBMS system, it's completely different. You put it on an isolation level. You tell that so we need the data to be replicated. All this, right? We wait for the response back at a very atomic level and tell that the data has to be very consistent. But whereas in the distributed system, we tell it totally in a different way. How much of right? If there are 100 nodes, we tell that acknowledges 3 or 4 nodes, that we tell okay. Then the other nodes would start replicating itself to the latest data. That is what is called, eventually it becomes consistent with the latest data that has been written by the latest nodes.
Okay.
Yeah, linearization, right? Linearizability, right? So it's so when someone speaks about this is more of theoretical. Normally, in anyone has in interview or when you speak, you do not speak about linearity, but at a very high level, and you want to understand how these concepts are brought in, then linearizability is the right word in the place of consistency. C actually stands for linearizability. So every operation takes atomically after it started and before it finished. So when we tell linearizability means that every transaction that you make
high level
is
and
very
you want to
atomic.
understand how.
So that a transaction T1, right? Say that T1 has written some data. When T2 comes, it has to see the latest data. It cannot see the data that was written prior to T1, which has already written. So that's the very high level when someone tells linearizability. So all operations behave as if executed on a single copy of the data, even if there are multiple replicas. So what does that mean? That when if I want to give an example, say that I make a profile update. Okay, so and there is a partition which has occurred. Now again, when I try to now when I'm trying to make a request, the request has to flow to the master and tell that where the previous request was written. I would read that data only. I would not go to a different follower TB or replicated data to get that data. So that, say, this is because the data would have been replicated or it would have not replicated. It may take time to replicate. So to avoid that, we tell that whichever writes you have made from your client, subsequent reads will go to the same server. So that's called write follows read, and that is more of an available system. It's completely all these right. All these are more of an available system. So as it goes top, right? As it goes top and top, it becomes more of your very strict consistency model. Subsequent reads will go to the even in the so even that's called all these right comes as part of the distributed system, whereas all these left side comes as part of your RDBMS. YogaDB, right, is why I put YogaDB is it provides you both distributed system and an RDBMS like structure. So that they have introduced read committed, serializability, and repeatable read isolations in your YogaDB, whereas a Cassandra does not has any of your isolations. So that's the difference. If you want to go read about YogaDB, you can read it because it gives you two flavors of distributed, and as part of RDBMS, you would be able to understand how they are trying to achieve that in a distributed system. And they're bringing transaction based in a distributed system, which is more like they're just following posters. Okay, so to address the other thing is why these are read committed or read uncommitted or more like available is because they do not block your calls. Anything that is committed gets read by subsequent request. Read uncommitted, right? Even in that, right? Where once say a process is locked row using an isolation level as read uncommitted, when a read request comes, it would be able to see the uncommitted data also. So it is more of available to you, even in the case of right in an RDBMS side. So once you go to cursor stability or repeatable read or snapshot isolation, right? See all these, right? Snapshot. I would explain you snapshot. Repeatable read, so repeatable read, because when once you lock a row, right? So that, and you're trying to the subsequent write comes to that, it would still wait until the previous write has been done, it will wait and then resolve the conflicts and then write it back. So that's why this is more of, it will be unavailable for you. You may not know what really happened, it may time out. All this may happen for the subsequent write calls. So that's why we tell it's more of unavailability than in the place of available. Yeah. So this is how actually your consistency model would look like when you're looking from a very high level, and when you want to really speak about very at isolation levels, how data has been replicated, what type of models do you want to use, then this chart, right, this would give you a better understanding of what type of consistency model should I use over availability, or this consistency model I will use and I would achieve availability. So that's how you need to think from a consistency model. Any questions here? Models do you want to use? Let me know if it is still complicated. Chart, right? This is even something very new to me, and even I recently learned as part of one of the presentation which was given as part of go to architecture conference.
Yeah, this also looks new to me, that I'm also trying to understand that, okay, how it is happening with the read uncommitted, and this. Once I will understand, then I can ask lots of questions at the just it is going there. Okay, I'm just understanding it.
So this is little, yeah. So this is more of consistency model. Even the consistency model, we are trying to achieve availability, but yeah. So this, when you speak about consistency, right? So there are problems where in a system design, right? They may go at very in-depth level, asking you what type of consistency would you use. So how would you replicate data? How would you how would I say there is a write, and how would I know that that write has been done and I want to subsequently read that write? So that is where you need to really memorize all these, that monotonic read, monotonic write, read your writes, and write follows read. All these concepts are very important in distributed system, because when the data is distributed, there are a lot of replications would happen. So I would tell you, so even now, right, if you go to your if you have Google account or any calendar, right, you want to check that really how things are happening. Just open your mobile Google Calendar and open it in the browser. You set up a calendar invite there, and just be you need to open your Google Calendar and wait and create an event in the in your browser, Google Calendar, and you just wait. Once you have created, right, then it takes some time to reflect on your mobile also. Then what you do is change something from the mobile end, and then wait, you would see the changes happening on the browser. So that is because it takes some time to synchronize all this. Then what you do is you put something in the mobile, right? Put your mobile into airplane mode, make some changes in your event. Say that you push it to 2 o'clock or 3 o'clock or 5 o'clock, or may create a new content. Okay, leave that as it is. Then go to the browser for the same event, change the date, and then leave it. Then what you do is then turn on the turn off the airplane mode and see what happens. You will see something different, because what you would see is whatever changes happened in the browser would start reflecting in your browser, and that the change that you happened in the browser, in the mobile, would not even take place. So that is because the last write also wins. So these are the things that distributed system works. This is how something distributed. I thought of showing you that example, but I was not able to record that in my mobile and my thing. It's a very interesting. You will see that even though you have changed first in your mobile, so that the event that you created in your mobile was the first event from a time point of view, but then you went and changed in the browser, which is actually something from your point of view. It looks like forward in time, right? You actually, the mobile change is the one is actually which should have happened first, and then your browser event should have taken place. That's what you would think, but it happens in a different way. Once you turn off the plane mode, it goes and checks, so the event is already there, and then it syncs up that, and then the other one that gets completely discarded. If you try that, you will understand how things are actually working in a distributed environment. And there are other scenarios. So like, if you start looking into YouTube's, right, after a certain point, they do not show all the number of subscribers in your YouTube. They start showing in Ks and in millions, right? They do not show completely. That is because once they would not be able to sync up everywhere. So you cannot have say that at 1 o'clock you have 5032 requests, and suddenly after 2 o'clock you see some other. After 2:30 you see the data to be different, and so that is because the replication is happening, and eventually it is trying to become very consistent, but it is not. So to avoid all these confusions, right, they show it in Ks and millions instead of just showing it in a what is the exact number. So there are because these are very huge systems, right? They tend to behave. So that's the trade-off that you start taking once you do all these type of things. Yeah. Okay. Let me go to the next slide. Yeah. So availability is the client can perform actions when there is a partition on a node. So that is. So what is that is, so within a cluster of nodes, right, say that all the nodes are not able to speak, but still the nodes are able to respond, then it means that the system is more of available. So we normally think that available as a binary states, but they are totally messy due to latencies. You're trying to update something and you do not get a response for a longer time, and maybe due to latency or slowness, or the node is down. So that is how, see, the availability in a node, right? So say that what we have told is that even in a cluster, once this within the nodes, they're not able to speak, but this node is up and running and you're able to get response, then we tell availability. What if a request gets fired and the system is slow and it is not able to respond? So what do you do? These are things that are not being addressed by CAP Theorem. That's what I initially told, right? Due to latency. CAP Theorem has a very narrow. You're trying to update something and looking at the system. You do not get a response. It does not look at a very broad due to latency, because there are a lot of other failures which can happen. So like the node may be very slow. It would have responded. The network congestion may happen, and you would have not got the response. Yeah. So there are a lot of other things which can happen even in a cluster, in a distributed system. So that's the problem with when you look from CAP Theorem. So other things are also need to be considered when you're not just speaking about when you speak about CAP Theorem. So how do you now find out, because you cannot indefinitely wait, right? The system may be available, or you may not even know what really happened. So the only way is that you set a timeout and you get a timeout. So at least you know that, yeah, I can fire another request and see whether really the system is responding or not. So that's about, as I do. CAP theorem does not, I repeat this because the CAP theorem does not speaks about the network delay, the dead nodes, or other trade-offs like slowness of the system. All this it does not speak. It tells that if there is a partition between two different nodes and if the node is able to respond, you're good. It means availability, but there can be other problems, right? in a distributed system. Yeah. Any questions here? Yeah, take it as yes. And for network partition is say that between two different data centers, right? A network partition has happened, but those two are able to respond you. So yeah, still they are able to respond. Then you're good. The system is in the event of network failure. So between two different data centers, the data you're able to get response from these two, but they are not in sync. But yeah, that is what is called network partition. So after the network partition is gone, the data gets synced up, and then it eventually becomes consistent. That's how people think about it. And the other one is network partition. So network partition is inevitable. It would happen, and you cannot stop that. And that's why people tell that when you look for a CAP theorem, you can only select any one consistency or availability, and partition tolerant always comes along with it, because you run a lot of cables between two data centers. Even within the data centers, right, we will have a segregation of two different things, okay, where the cables would be running between two different data centers within the same environment, and something happens within the same data center itself can get disconnected. The data would be flowing in and out, but they would not be in sync. So it's like telling let the client keep writing in both the sides of the split. So once say that there is a partition which has occurred between this and this, say that it's partition has occurred in between these two, and they're not able to sync the data between these two. But the request which comes here to read and write, keep on writing here, and keep on writing here. Once this happens, right, your linearizability goes off. Your consistency is no more available. You cannot achieve consistency using partition network at all, because consistency means you tell that any data that you write is I would tell that it's more of the next subsequent read has to see that data. That is what it means. So, but whereas in the partition tolerant record, you'll never be able to see that. And so if you stop writing, right, say that no, there is a partition network occurred, and now I do not want things to go out of sync, then you are sacrificing your availability. You will not be able to accept requests, and then you will start throwing errors, and all this happens. Then things become messy here, and you sacrifice your availability. So to know exactly why network partition cannot be discarded, right? There is a paper written by Jeffy Dane, who's a vice president at Google. So when Google started moving from traditional to cluster-based systems, he has told that in a year they will see 5 rack failures, 3 routers failures, and 8 network maintenance happening. Okay, so and the hardwares that are built are not 100% failure proof. You cannot make, because you may not know when the hardware would fail. So even now, right, even at SAP Cloud, we see that we get mail saying that one of the cloud environment is down, and people start fixing it. And you would have seen yesterday, there was I think the Roker or the Canadian Telecom just went off. It took almost 1 day to recover from it. So then there is another one, so you would have known that there was outage on by the Cloudflare, which has happened, and there was an outage by even by Amazon. There was an outage which has happened by Facebook. So there was an outage done by Acme, which is a CDN, which again caused by network. So these are some things which we tell more towards like network and things, but there are there are certain things which CAP theorem does not address, right? Like software outage. Software outages is not even spoken by CAP theorem. And the Cloudflare, which I told, right, was a problem in the configuration which some engineers did, and the entire Cloudflare was completely, it was cut off out of the network. It started. I probably guess there is a very good article written by Cloudflare. What was the reason? What really went into the configuration files and how they missed in the review. All this. So why when a request comes, why it was getting routed into a different thing where it never even landed. So those things it does not speak. Okay, so it's a very if you want to really understand theoretically, these are the things that you need to understand theoretically. But when you speak from an when you go to an interview, right, when they speak about CAP theorem, you just need to tell, yeah, it's more of availability or consistency or network partition. That's it. But if you really want to design a system, then you need to go beyond CAP theorem to understand how to build a system. Because CAP theorem will not help you to build a complete available or consistency system. That's the problem with the CAP theorem. Um,
So yeah, Manoj, one input here, and this is important one. I have experienced this, and I also expect everyone whenever you are in a system design interview, and any question you are asked, first thing what you should do is use the CAP theorem and figure it out what kind of system it is. Is it about consistent system which is being asked in the question, or is it high availability system? And then you use this trade-off between the consistency and availability and put forward your solution on that principal foundation. So this way you will be able to the point, and you will be able to design, and you will also be able to prove your architecture skills.
Yeah, that's right. Yeah, from an interview point of view, yeah, you just need to know what is captain. That's it. But you do not need to know in depth on linearizability, because linearizability speaks a lot more in depth how a system can be very consistency. So it does not even speaks about just in a distributed system. As I told, linearizability speaks when you are trying to build something on a single state machine also, when there are concurrent data getting accessed. So that's what, if you want to theoretically understand, and they are theories, but still they are being applied practically at a very low level. When you want to really build a complete, you want to architect a very good system to a production, right? Yeah, you need to know linearizable, because you need to know what isolation levels to use. You need to know how the data should be read moving forward, whether it has to be monotonic read or monotonic writes, or it has to be read your writes, or read follows writes. All this, yeah, in depth you need to know, because sometimes, right, say I was asked a question in Walmart, so how do you design a system where you have stores and people order, and you need to have you need to give the customers a slot. So the slot is very fixed. It's for every hour there's only 100 slots available, but the problem is 100 slots can get immediately booked at within a second it can book. But the problem is, once the data is read right, the customer is trying to book that, he may get into an error, say the slot has been already booked, and he has to be shown. So how do you do that things? So that's where these things come into place. This linearizability. I was explaining him that monotonic read is the only possible solution that you would be able to do, and you need to have multiple replicas of data. One is for write and one is for read. So you always read in a forward direction. So monotonic reads and monotonic writes are the only possible ways here. So yeah, so exactly the one which I explained, that is what for he was looking for. Yeah, but yeah, so it depends on the interviewer also, how what he is looking for. If you do not know what is monotonic read or monotonic write, then probably it would be very difficult to explain him what are those and why, how consistency levels are being followed, how can we achieve them. Yeah. Yeah, again, yeah, I probably assume in the previous class I told, right? All these information that I get as part of CAP theorem or as part of linearizability, I read them from Martin Klipman's book. You really want to understand how CAP theorem and Martin Klipman books. Martin Klipman has given a very good introduction to CAP theorem and linearizability. He speaks in very in depth. Probably that's unneeded, but yeah, still theoretically you will understand in depth, and when you're speaking in the meetings, you'll be able to grasp things, and you'll be able to suggest a lot of problems that you can address upfront when you're trying to design a system.
Can you tell that what is the book name, Manoj?
No, Martin Klipman is the author. It's called Designer Data Intensive Application.
Design Data Intensive Application. Okay.
So he speaks about replication lag, all these. He speaks about replication lag. He speaks about single master, multi-master, leaderless things, and problems with replication lags. All these he speaks. So it would really give you an understanding how behind the scene the database are built. So even the Yogabyte DB, right? If you go to Yogabyte DB, you would find a lot of blogs written by the founders and founders of the Yogabyte DB. They would have written a lot of articles how raft consensus algorithm is being implemented in their DB, and how they are trying to achieve consistency in a distributed system. They give you a very insight. I probably guess that was one of the where I studied a lot of things about the distributed system. And you need, yeah. So the one thing why I recommend them is because the people who are building the Yogabyte DB is the people who built Cassandra at Facebook. Yeah, I would give you the link for them also, so because and yeah, you want to understand how Facebook stores profile information. They still store it in MySQL only. The underlying thing is MySQL. They have something called TOA object, is an object association which is written on top of MySQL. So that's a very good blog written by the founder who was leading that project, and he now the same guy who has started the Yogabyte TV has written a very good blog on how Facebook stores the information. Okay. Probably yes. Yeah, you can look into this also. This gives you an insight how does it use. Yeah, he starts saying that, but you'll have an insight. Still, they use MySQL, and there is a talk even given by Facebook how they store data. You can look into that also. So they follow a different concept, saying they write into the follower and then they write into the master, and then that gets written into the master of the MySQL. You can have you can go over that document. It speaks very in depth, and as I told you, right, they use an object called TAO object, which is built by Facebook. It's like a graph, which speaks in depth, and that blog speaks in depth about it. Yeah, I probably guess I'm done.
Yeah, one more question, Manoj. You told about that some of the architectures conference you went there and you learned from there. So which architecture conference you went and learned?
No, I have not gone to architecture conference, but there is something got in YouTube. You have a lot of things. You in YouTube you have something. There are multiple channels. Okay, so you have like go, you have something called go to. It's an architecture conference. Go to conference they call it.
Okay.
There are a lot of architects who comes and speaks about each and every design, or they speak about microservices, problems with microservices. And there is another one, Dev DevOX conference.
Mhm.
DevOX conference, and then you have InfoQ. You have InfoQ. So in InfoQ, you'll see a lot of the world things like about Netflix, and you would be able to see them. So these are the main three things I generally follow. There are other things also. And other thing is, if you follow each and every engineering blogs, right? Like you can follow Facebook engineering blog, you can follow Instagram engineering page, you can follow Twitter engineering page, Google engineering page. Google does not have directly engineering page, but yeah, they write blogs which are more of you search and you will be able to see they come from the blog. Like it's more like tutorial, but you'll have a lot of information on that. Then I even follow for DB, mainly I follow FYDB because those guys are implementing new things and they tell what are the difficulties in they are facing and how it is hard to achieve certain things in a distributed system. Would give you an understanding how, because they are something very new in the market and they're trying to do a cloud-based distributed system. So how are they trying to achieve? They have every Friday they give a presentation on things that they have newly implemented or things that are going to get released, how internally things work on a distributed system they speak. You can follow that. Yeah, probably I'm done, Tarun.
Great. Nice presentation, and if you can share this also, that will be great. And you have nice diagrams, all are visual presentation, so that's great. So
Yeah.
thanks, Manoj. And one more thing I just wanted to add. There is also very good video about Pinterest architecture. That's something also, I will recommend everyone watching. Have you watched that Pinterest architecture session, lecture session, which is there?
Can you just ping? Let me see. Because I see a lot of things in a day.
Yes.
Day and on Saturdays and
So
Sundays.
these are this is not very recent. It's I would say pretty old conference, or there was a session, and in that the founders of Pinterest, they shared their experience of designing Pinterest, and they designed it from scratch, and it was one of the first large scale applications in the web which was very successful. So they talked about what they achieved and how they scaled up from 10 employees to 100 employees, and what were their
Okay. I have
challenges.
seen this for the other one, right? Where the Reddit, right? You have the Reddit, right? So that was developed at the college, and how did they scale? There is one presentation which was given by the founders. How from a single system they went on to buy additional. It was actually built on laptop, from laptop, how they moved on to become a bigger company. They explained how gradually they moved on, how they started introducing distributed systems, how they found that a single system cannot scale. All this they speak, and that's also a very good video. I probably guess it's part of the InfoQ series where you can search and get.
Okay, okay, great, great. Sure. So yes, no, I have shared about Michael Clapman's YouTube playlist as well. So he
I
has also made all his lectures on distributed systems available in his YouTube channel. So the name of the YouTube channel is
yeah,
Martin Clapman. Yeah, and he is a professor at Cambridge University who takes distributed systems classes for computer science engineers or so he has good content there, and no, of course the book is also good. And then there are many people who have shared their summaries of the book, because that book is the very book, and it's difficult to understand in the first reading, so you have to go through it multiple times. It's very technical book. So yes, people have a lot of sessions shared around that book, so that would also be very helpful. No, I would suggest initially going through these concepts as explained by different viewers in layman language. That helps more.
yeah. So yeah, that book, right? It's very difficult to understand if you're not worked on a really high scale distributed system, because even I do not have experience. I have to study twice to understand that book completely once again, uh, because certain concepts you would have never even thought it could occur like this. That's what I told him. He gives a very in depth, a very low level and a granular level to think about how a database would behave in a distributed system. Then, when you think about a traditional database and you speak, when you would have implemented a lot of, I have implemented a lot of database applications. But we have used isolations like repeatable read, all these concepts for implementing them. And I never even thought of all these problems in a distributed system when I started reading his book. After that, it gives you a very good understanding how really in a distributed system things have been put in place, because it's geographically distributed. All these, right? So when you're designing a system, you would be thinking of one data center and things working there, but within a region itself, you'll have multiple data centers, and those data centers should be connected somewhere in. Say that you design it for US, then something for Europe, then you start designing it for Asia. How do you sync up all these data? So he speaks about replication lag, all these concepts. Even now, if a node goes down, right, in a leaderless database, right, like Cassandra, all these, right, they take seconds to decide who should become the leader. By the time you have n number of requests, which is also lost. So there are a lot of complexities. He speaks about that, and then he tells how researchers are still going on in those areas. Yeah, so still there is research done in those areas. If people are there who are newly joining computer science, you can suggest them to join in the research field, because there is a lot more work to be done in the distributed system of research.
Great, great.
So, one question here, Manoj. Which book you are talking about? Is it data intensive application book, correct?
Yeah.
Okay.
There are a couple of other books also, but his book is very good.
Yeah, that's book's very good. Nice.
His book. There are other couple of books also, but his book gives in-depth knowledge into the database side. So, and also on the batch perspective also, because Synchronization is something different from your batch process. Okay, batch is more complicated than your synchronization process. There are a lot of other complexities when you start building a batch application. So he speaks about that also. At the last chapter, he starts speaking. There's one chapter where he speaks to batch processing and things. That comes at the last, but yeah, he speaks very intensively on those side also.
Okay.
Great, great. So yes, we'll have this sessions every Sunday 2:30 p.m. So we can use the same invite, and even if no, I'll mostly share what is the agenda. But yes, in case you miss out checking the WhatsApp, you can just make a schedule that 2:30 we can discuss on system design some topics. So we started discussing distributed systems. That track we can continue. CAP theorem also nice. We can go through various practical systems design as well. So please feel free to suggest topics. And I also gave a presentation about cloud native applications so last time. So we'll continue that also in next few sessions, right? And then I also recommend maybe on the database side we should also start one track where we can discuss database designs, because that's also very important topic and different. So we are working with distributed system, mostly deals with how to have computing in a distributed way to increase the throughput and scalability. But then how to have good database design, data modeling, and concepts related to SQL and NoSQL databases, that also we can start discussing in these sessions.
Yeah, so yeah, I think we can speak about more of distributed databases
Okay.
because yeah, then we can go back. Then we can slowly, gradually move on to RDBMS, probably because it's like knowing about if you want to when should we use Cassandra, when we should use RDBMS, when should we use HBase, or when should you use MongoDB. I probably guess that session would give you an insight into when and where to choose a database. So that would give you a little understanding. If in the interview, right, sometimes they ask you what type of database would you use. Like when you tell consistency or availability to a system, they'll suddenly ask you what type of database would you use, whether you will use NoSQL or you will use RDBMS. If it's once you tell NoSQL, then they'll start asking you what actual DB will you try suggesting. So those
Right.
things, yeah, come up in the interviews. I face such things. Yeah.
Okay. Great. So
Because understanding the database is more important. People look at that side, more focused, because that's the state where all your actions are being stored, right? And you're trying to get those actions back. The other in between system is more like processing, right? It's more like computing things and sending back. The more complexity lies on the database side and the application that is trying to write and read those things. And
great.
then I think probably then we can move on to distributed cache because caching is also very vital. And there are a couple of caching techniques like you have for write also, and you have mostly there for read. So we can speak about that also.
Sure, sure. Great. So then one more thing which I'll do starting next week is I'll make these sessions available in live also, so that people who wants to interact more frequently within the session, they can join this Google Meet invite. But if someone is not feeling well, or he just want to be in and out, or just watch it in relaxed mode, for them, we'll also share this videos. We are sharing already recording, but I'll make it available as YouTube live event as well, so that many more people can join and take benefit from these sessions about learning system design. Great. Then if nothing else from anyone, we can close this call, and we'll again meet up next Sunday, same time.
Yeah, we'll close up this call.
Yes.
Thanks to everyone. Thank you. Bye.
Thanks, Tarun.
Sure. Thank
Thank
you,
you, Manoj.
Manoj.
Thank
Thanks
you.
all.
Thanks to